Welcome to Let's Talk podcast series by the Electrochemical Safety Research Institute of UL Research Institutes. In the Let's Talk series, we host the leading experts, scientists, and engineers focusing on energy storage systems, safety science, and standards, and learn about their experiences and visions. My name is Byung-Chul, and I will be your host for this episode. Today, our discussion is focused on the fire safety of lithium-ion batteries. Lithium-ion batteries are now widely used in many applications such as portable electronic devices, electric vehicles, and energy storage systems for renewable energy. However, we are also observing an increasing number of fire incidents related to lithium-ion batteries, and these fires can be difficult to control and extinguish. Today, we invited Professor Ya-Ting Liao to understand the lithium-ion battery fire. Professor Ya-Ting Liao is an associate professor in the Department of Mechanical and Aerospace Engineering at Case Western Reserve University. Professor Liao is leading the UL Fire and Combustion Laboratories and the Computational Fire Dynamics Lab at Case Western Reserve University. She has been studying a wide range of experimental and numerical fire science topics, including solid pyrolysis in ignition, structural fire, wildfire, microgravity combustion, and lithium-ion battery fire. Ya-Ting, welcome to our podcast, and thank you very much for being with us.
Thank you for having me. My pleasure.
You have been studying fire science for many years, so could you tell us what motivates you to study battery fire?
Yes, thank you for the questions. As you mentioned in the introduction, lithium-ion batteries really have become very popular in the past few decades. This is because they have many advantages. For example, high energy density, they are relatively low maintenance, and they have long lifespan. These features really made them a promising energy storage technology. But as you mentioned, in the meantime, we have seen a substantial increase in fires and explosions related to thermal runaway of lithium-ion batteries. Let me give you two examples. Just a few months ago, in November 2022, an electric vehicle caught fire in central Pennsylvania. In this incident, 12,000 gallons of water were required to extinguish the fire. To put this into context, this amount of water is about 24 times of the water that were used in a typical car fire. Another similar event, this incident occurred in Queens, New York City. An e-bike caught on fire when it was charged near the front entrance of a multi-family building. According to New York's fire department, firefighter actually got to the scene within 3 minutes, but the fire was so intense and spread very fast up the stairs to a second-floor apartment. This tragic event eventually took the lives of 2 youths. These are just among many incidents we saw on the news, almost like daily basis. I use these examples to just to demonstrate the importance of gaining a thorough understanding of lithium-ion battery fires. This is the motive of the battery research in our lab. Through research, we hope to help address the fire safety concerns and ensure the safe utilization of batteries.
Thank you for the answer. To help us understand fires, can you please talk a little bit about the physics of fires and how to suppress a fire?
Yes, conventional fires mostly involve solid materials. For example, building structure materials, wood, plastic, and trees. When subject to heat, this material can reach their pyrolysis temperature, or we call it decomposition temperature. After that, this material decomposes and releases flammable gases. When the flammable gases mix with oxygen in the air, combustion can occur. This is how we have a new fire and how fire spread across solid combustibles. We usually illustrate this process using a fire triangle. This fire triangle consists of the 3 required elements of the fire to occur. They are heat, fuel, and oxygen. To stop the fire, we just need to remove one of the 3 elements from the fire triangle. For example, we can spray water to remove heat. The water can also cool down the solid combustible and stop the generation of combustible gases. We can also apply carbon dioxide extinguishers to separate the oxygen from the fuel surface. Based on this principle, a lot of different fire suppression techniques have been developed, and they have been working very well in the past few decades.
Thank you. What is the difference between the conventional and battery fires then?
Right. So battery fires are relatively new to us, and they ignite in a very different way compared to the conventional fires. Like, for example, lithium-ion battery fires can occur when the cell electrochemistry is disrupted. This can be caused by overcharging in abnormal operating circumstances, such as external short circuit, rapid discharge, overcharging, and physical damage of the battery cell. This can also be due to manufacturing defects or poor design of the batteries. This event can cause the decomposition of the solid electrolyte interface. After that, highly exothermal chemical reactions occur between electrode materials and the electrolyte. When the heat produced in reactions exceeds the heat that can be dissipated on the cell surface, a rapid rise of the cell temperature can occur. This process is referred to as thermal runaway. During thermal runaway, gas products can be generated inside the cell. When that happens, pressure builds up inside the cell, and eventually the cell can rupture, and highly flammable and toxic gases are released rapidly. This can be a very catastrophic event, especially when the multiple cells are involved.
Then, do battery fires introduce more challenges compared to conventional fires?
Indeed, they are more challenging compared to conventional fires for many reasons. First, early detection is not easy. When we observe gas venting out of a battery, thermal runaway process has already occurred, and they cannot be reversed. Second, suppression is extremely difficult. During thermal runaway, not only fuel vapor, but also oxygen can be generated inside the cell. Therefore, we cannot remove the oxygen component from the fire triangle. Heat is also being constantly generated from the thermal runaway process. This further increases the difficulty to suppress the fire. As we talked about it earlier, significantly larger amount of water is needed to suppress the battery fires compared to conventional fires. Even when the battery fire is suppressed, reignition can repeatedly occur due to the heat generation inside the cell. This reignition phenomenon is really dangerous and makes firefighting even more challenging because it can suddenly occur after firefighters believe they have already put out the fire. It has been observed in many electric vehicle fires. Another challenge about battery fire is that the gas released are highly toxic. In addition to that, application of waters or the other fire suppressants may result in hydrogen fluoride. If not handled properly, these toxic gases pose great threats to human health.
Thank you. Can you give us a brief overall description of your research on battery fires?
Yes, in our lab, we study battery fires both through experiments and numerical modeling. We know that the severity of fire hazard is mainly dependent on the nature and the composition of gases released during the thermal runaway. There have been many scientific research on lithium-ion battery thermal runaway process already, but we need more experimental data to develop a robust numerical models. For example, real-time measurement of cell temperature, mass, gas compositions, and the visual images. So in our research, we are particularly interested in real-time gas composition analysis because it will provide valuable, important data to develop a robust gas phase combustion model.
Can you talk a little bit more about your experiments?
In our experiment, we have two major objectives. First, we really like to characterize the smoke and fire behaviors associated with the thermal runaway process. And second, we would like to provide real-time experimental data that enabled development of numerical models for battery fires. To achieve these two goals, we perform battery fire experiments inside a 600-liter environmental chamber. We make sure to condition the battery cells to a desired state of charge before each experiment. And then the cell is set up inside a chamber on a sample holder. Finally, the battery is forced into thermal runaway by an electric heating tape. So one thing that I would like to emphasize is that our chamber is connected to a Fourier transform infrared gas analyzer for in situ gas sampling throughout each experiment. Our gas analyzer currently detects 21 gas species, including various hydrocarbons, carbon dioxide, carbon monoxide, hydrogen fluoride, acrolein, and formaldehyde. In addition to that, we have a standalone hydrogen sensor installed in the chamber because we also want to record the hydrogen concentrations. So gas analysis is the main objective, but in addition to that, we also measure various other parameters. For example, cell surface temperatures, cell mass, voltage, and chamber pressure. And of course, the entire burning event are recorded by camcorders from 2 different angles.
What is the most challenging thing in your experiments and how did you overcome it?
The biggest challenge definitely is the toxicity of the vent gas during thermal runaway. Safety is our top priority, and we spend tremendous efforts on implementing multi-layer measures to ensure the safety of our students. For example, we use sealed chamber to confine the exhaust gas during our experiment. And prior to each test, we always conduct a vacuum test to make sure the chamber is really airtight. Even though gas leak is not expected, we also require students to wear proper respirators during the entire tests. Students are also encouraged to move to another room and monitor the experiments remotely during the experiment. We developed a detailed post-test chamber cleanup procedure and make sure to filter and pump the chamber gas directly to the building exhaust line. One thing to know is that in our experiment, we detected various toxic gases, for example, as I mentioned earlier, acrolein and formaldehyde. Although these gases account for a very small portion of the vent gas, but we know that even very low concentration of these toxic gases pose great threat to human health. OSHA imposes occupational 8-hour exposure limits of 0.1 ppm for acrolein and 0.75 ppm for formaldehyde. These values are significantly lower than the values we measured using our 600-liter chamber. This further emphasizes the toxicity hazards of lithium-ion battery fires. This also further highlights the need to have a test method for characterizing toxic gases released for the lithium-ion battery.
Can you talk about how your experimental data can be used to help model development?
Yes, we have a parallel effort on numerical modeling. As you know, battery fire is multi-scale and multi-physics. So simulating details of every single component of the event can be extremely expensive and sometimes even unattainable. For this reason, we would like to take the advantages of experimental results and use them to replace the simulation of the electrochemistry of the battery cell. To do this, we first used the data obtained in the experiment to deduce compositions and the mass rate of the thermal runaway gas. They will be expressed as functions of cell temperature and cell state of charge. These deduced functions are then implemented into a computational fluid dynamics model as boundary conditions. This removes the need to simulate the electrochemistry of the cell and allow less assumptions to be made. This will result in a more general, numerically cost-effective and precise model for battery fires.
Thank you for the answers. Given your extensive fire research in a microgravity environment, I would like to ask how you expect battery fire behaves differently compared to ground fires. So if we run experiments in space, what would it look like?
In microgravity, one major thing you can expect is that buoyancy flows are not there, is eliminated. This will have two major impacts on the battery thermal runaway process. First, the lack of buoyancy convection cooling causes a reduced heat loss on the cell surface during thermal runaway. This implies that the battery can potentially go into thermal runaway at a faster rate or at a lower temperature. Second, without the buoyancy flow, the released gas and combustion products are harder to dissipate. This can lead to even more serious toxicity concerns. And we have also seen that for fires in space or in microgravity, fire tend to stay closer to the combustibles. In this case, would be closer to battery. This leads to larger heat feedback from the battery fire to adjacent battery cells. And this can facilitate the propagation of thermal runaway. All these implies that a battery fire can be more destructive and dangerous in microgravity than in normal gravity.
Thank you very much, Professor Liao, for taking time and sharing your perspectives on lithium-ion battery fire research today. Thank you for listening to Let's Talk.